Welcome to Scaling Up Microencapsulation with PLGA. What really happens behind the scenes? Today, we're going to explore what truly changes when you go from a small laboratory beaker to an industrial-scale reactor. And trust me, this journey isn't just about bigger equipment, it's about mastering an entirely new level of engineering, chemistry, and problem-solving. In the lab, PLGA microencapsulation feels almost magical. You work with small beakers, predictable conditions, and nicely controlled parameters. Everything behaves the way your protocol says it should. But when you step into industrial scale, that magic disappears fast. Suddenly, you're dealing with large reactors, uneven mixing zones, unpredictable fluid dynamics, and variables that don't scale the way you expect. And that's when you realize, scaling up PLGA microencapsulation isn't magic. It's engineering, chemistry, and plenty of troubleshooting. One of the biggest reasons scale-up becomes complex is that PLGA doesn't behave the same way when volumes increase. In small beakers, shear, diffusion, and solvent evaporation are easy to control. But in reactors that are 100 times larger, these same factors behave completely differently. Shear fields become uneven. Mass transfer slows down. Solvent evaporation becomes difficult to control. Droplet breakup changes dramatically. And almost every parameter that mattered at small scale refuses to scale linearly. So the real challenge isn't making the process bigger, it's redesigning the process to fit the new scale. I once worked with a team trying to scale the classic WOW double emulsion method. At 50 milliliters, everything looked perfect. Tight particle size distribution, beautiful morphology, and excellent drug encapsulation. But when we moved to a 5-liter batch, everything fell apart. Instead of uniform particles, we got a chaotic mixture of oversized aggregates and ultrafine debris. That's the moment you realize that scaling up isn't just turning the knob on volume. It means rethinking the entire process. At 50 milliliters, we consistently produced particles around 1 to 2 microns in size, with encapsulation efficiencies near 90%. Clean, predictable, reproducible. But at 5 liters, we saw the complete opposite. Poor reproducibility, inconsistent particle sizes, and encapsulation efficiency that dropped dramatically. The system just couldn't maintain the delicate balance required for stable double emulsions at that scale. Mixing and shear are silent saboteurs during scale-up. In lab-scale systems, small impellers and uniform shear produce predictable droplets. But in large vessels, shear becomes uneven, calm at the surface and highly turbulent at the bottom. And here's the key insight. PLGA droplets remember the shear environment they were created in. The biggest mistake most people make is trying to match RPM between scales. That never works. Instead, the correct strategy is to match tip speed and energy dissipation rate, because these are the real forces that control droplet breakup and particle size. Solvent removal is one of the most underestimated challenges during scale-up. At 50 milliliters, solvent evaporates quickly and evenly. You get consistent particle hardening and predictable porosity. But at the 5-liter scale, solvent removal becomes slow, uneven, and messy. This leads to inconsistent porosity, variable drug retention, and unpredictable release profiles. To fix this, we switch from passive evaporation to controlled solvent extraction. We increase aqueous volume, use continuous flow systems, and apply inline solvent monitoring. These tools help maintain consistent hardening and preserve drug integrity across large batches. At some point, every team trying to scale up PLGA realizes that the old stir and pray method simply won't work. So we turn to advanced droplet formation technologies. High-pressure homogenizers offer high throughput but less control over droplet size. Microfluidic arrays give you exquisite precision, but throughput is limited. Membrane emulsification strikes a balance. Excellent uniformity with good industrial scalability. Choosing the right technique is like choosing the right vehicle for a road trip. You don't ride a bicycle across the country. The method has to match the scale. When scaling up, the internal structure of PLGA particles changes. Hydrophilic drugs in WOW systems are especially sensitive. The inner aqueous phase behaves differently at large volumes, leading to drug leakage and lower encapsulation efficiency. To overcome this, we adjust the viscosity of the inner phase, optimize stabilizers like PVA, modify PLGA molecular weight or end groups, and sometimes even switch to phase separation techniques for difficult molecules. And once we stabilize formulation, we shift focus to reproducibility and quality. That means implementing inline sensors, PAT tools, validation protocols, and continuous feedback loops. That's how you turn an artisanal lab recipe into a world-class industrial process. Finally, remember that scaling up isn't your only option. Sometimes scaling out, running many small optimized units in parallel, gives you better control and higher consistency with far less risk. When you truly understand the physics behind PLGA microencapsulation, scaling becomes a craft. It's a journey full of surprises, redesigns, and breakthroughs. In the end, it's not about making more particles. It's about making them consistently, predictably, and beautifully, at any scale.